Good morning, everybody. Today we will continue with temperature and heat, very important for engineering and also for basic science, and also very important for industrial applications. So usually, if you are doing something, you should know what is the temperature at that conditions. And today we will discuss how to use different temperature measurement systems, and we will discuss the relation between temperature and heat. So we will learn the meaning of thermal equilibrium and what thermometers really measure. We will discuss different types of thermometers, and we will discuss the physics behind the absolute or Kelvin temperature scale. We have different temperature scales. We will discuss them. And then we will learn how the dimensions of an object change as a result of a temperature change. This is thermal expansion or thermal shrinking. So the shape of the object changes as a function of temperature. This is also very important for industrial applications, for engineering applications. And in the next part, we will learn how to do calculations that involve heat flow, temperature changes, and changes of phase. And finally, we will finish how heat is transferred by conduction, convection, and radiation. So with this one, we will finish this chapter. Let me start with the temperature and thermal equilibrium. We use thermometers to measure temperature. Here on the right side, you see a thermometer, very common one. And within the thermometer, we have a volume. Within this volume, there is a liquid. It can be mercury or ethanol, okay? In addition to that, this thermometer is made from thin glass wall. Why? It is required for the thermal equilibrium, for fast thermal equilibrium. And here we have thin glass wall in this part, but here we have thick glass wall. You see, the wall of this part is thicker, and we have capillary of small volume here. So if you put here a heat source, then the temperature of this liquid here will increase, and then the volume of this liquid within this thermometer will increase. Then you will have new level here, and this part will also be filled. Or if you use a cooling source close to here, then this level of the temperature will decrease. It will come somewhere here because due to the cooling, the volume of this material within this thermometer will decrease. So this is the general working principle of glass thermometer. But here we have very important term, thermal equilibrium. So you would like to measure the temperature of some object or body, then you use this thermometer. So let's consider that here there is a body, okay, or here there is an object, and this thermometer and this object are very close contact. They touch to each other, okay. So this has certain temperature T1, and this thermometer, the liquid within the thermometer has T2, okay, before they touch to each other. And after certain time, if they touch each other, after certain time, T1 will be equal to T2, okay. So this is the thermal equilibrium. And then the temperature of the liquid within this thermometer will be equal to the temperature of the body here on the left side. And then if the temperature on the left side, T1, is higher than the volume of this liquid within the thermometer will increase, and then the temperature within the temperature scale, you can read the actual temperature of the body. Then let me discuss gas thermometer. So this is a container of gas at constant volume. Here we have a container. Okay, it has constant volume. Its volume cannot change. Okay, and we have a gas within this volume. And if you use a heat source, if you increase the temperature of this gas within the container, then the pressure of this gas will increase. And here we have a pressure gauge. Okay, you measure the pressure, and this pressure you read on the gauge is proportional to the temperature of the gas. So you can use the container of gas to measure the temperature. So changes in temperature cause the pressure of the gas to change. Do you have any question here? And we have very common thermometers used in industry, used in engineering, and also used for scientific purposes. Here we have platinum thermometers, and here we have Cernox thermometers. This upper part belongs to the platinum thermometers. Platinum is a metal, okay, and metals have this type of behavior with the temperature. This is the temperature in Kelvin, and this is the resistance or resistivity of the material, okay? And in case of metals, there is this type of behavior. So what do you see here? When you increase the temperature here on the right side, we have a region which is very sensitive to the temperature. You increase the temperature, then resistivity increases. You increase the temperature, then resistivity increases, okay? Here at low temperatures, let's consider this is the 0 Kelvin and this is, let's say, 1000 Kelvin, okay? At low temperatures, these thermometers, these metal thermometers are not so sensitive to the temperature, okay? So you increase the temperature, but resistivity does not change so much. Here, resistivity does not change so much. But at high temperatures, metal thermometers, platinum thermometers are very sensitive to the change in the temperature. So these are the different platinum thermometers from Lakeshore, one of the main temperature sensor producer and temperature controller producer in the world. And we have few of them in our laboratory. And here you see a common resistance versus temperature graph of these thermometers. What do you see here? This is, let's say, around 30 Kelvin, something like this. And here you see 10 Kelvin, okay? And in this region, the sensor, the platinum is not sensitive to the temperature changes, but at high temperatures, they are very sensitive to the change in the temperature. So here we have 100 Kelvin and we have this resistance. Here we have many 100 Kelvins and here we have this resistance, okay? So by measuring the resistance, you can get the idea about the temperature. You can measure the temperature. So what do you see here? In reality, within this part, there is this type of coil made from the platinum, and we measure the resistance of this platinum as a function of temperature, okay? So resistance gives us information about the temperature of the system. These are also called as resistance thermometers. Okay, and in Cernox thermometers, semiconductors are used. Okay, and semiconductors have different temperature relation. This is the resistance of the semiconductor. Let me clean the upper part, and then you will better see the difference in between. This is the resistance versus temperature curve for metals. And as I told you, they are very sensitive at high temperatures. And in case of semiconductor thermometers, at high temperatures, they are not so sensitive to the temperature changes, but at low temperatures, semiconducting sensors are very sensitive to the small changes in the temperature. Okay, so here, for example, you cool this sample down to this temperature and you have this resistance, and if you further cool the sample down to this temperature, then we have this resistance. So we have huge resistance change in the Cernox thermometers, in semiconducting thermometers, and there are different shapes in the Cernox thermometers. Again, you measure the resistance from these arms, you measure the resistance from these arms. Okay, there are different types of designs. Here we have, again, resistance versus temperature curve for Cernox thermometers, and depending on the thermometer type, here you see different Cernox numbers produced by Lakeshore. They have different resistance versus temperature behavior. What do you see here? At low temperatures, they have huge change in their resistance due to the temperature, but at high temperatures, the change in the resistance as a function of temperature decreases. So these are the metal and semiconducting thermometers, and by using these thermometers, you can measure the temperature. So we are talking about temperature, we are talking about thermometers, and these are also thermometers widely used in industry. Very important, very stable thermometers. And there are also infrared thermometers. These thermometers includes an infrared detector here within the thermometer, okay? And you don't need to touch to the system. So in case of this glass thermometers, so this body here should touch to the thermometer. In case of this container, body should touch this thermometer. In case of this metal and semiconducting detectors, body should touch to the thermometer. But in case of infrared detectors, infrared thermometers, touching is not necessary, okay? These thermometers can measure from far from the body, okay? So I will go into detail related to the working principles of these thermometers, but they are also very widely used for everyday life. And class is infrared thermometers. Another type of thermometer is a bimetallic strip. Here in picture A, we have a bimetallic strip made from two metals. This is the metal 1 on top, okay? And at the bottom, there is another metal, but they are different metals, okay? With different properties, with different thermal properties. So if you use a heat source here, if you heat the material, then this bottom metal, metal 2, will expand, and this upper metal, metal 1, blue one, will also expand. But since they have different thermal expansion properties, then you will have this type of shape, and you can measure the temperature by using this type of bimetals. And here there is a thermometer on the right side, a spring, spiral spring made from a bimetal used here within this thermometer. Okay, so we have a scale here in degrees Celsius, you see, from 0 to 100 degrees Celsius. And here we have a pointer, and this pointer is attached to a spring, and this spring made from bimetallic strip. Then, as a function of temperature, due to the thermal expansion, the shape of the spring changes, and then you can measure the temperature by using this bimetallic strip. This is another type of thermometer, and with this one, I finished the types of thermometers. So depending on the application, you can use these thermometers. Do you have any question up to this point? Now let me discuss the thermal equilibrium. What is thermal equilibrium? This is the zeroth law of thermodynamics, and it is related to the thermal equilibrium. Here in picture A, we have a system A or material A, okay? And here on the right side, we have system B or material B. And at the bottom, we have system C or material C. And between system A and B, we have an insulator. Let me use another pen color. Here we have an insulator. This is thermal insulator, okay? So this material is used to insulate these two systems, okay? System A and B. So this system has certain temperature, TA. This system has certain temperature, TB on the right side, and system C has also certain temperature, okay? And here, let me use another color. We have thermal conductor, okay? Between system A and system C, we have thermal conductor. So this system A and C can interact thermally very well, okay? Because here we have thermal conductor, and between system B and system C, there is also a thermal conductor, okay? So heat transfer can happen easily between B and C systems, also between A and C systems, but between A and B, we have a thermal insulator, and heat transfer is blocked, you can say, okay? So if systems A and B are each in thermal equilibrium with system C, so what I have told you that, let me use another color here. Here we have on the left side system A, at the bottom here we have system C. And these two systems, system A and system C, are in thermal equilibrium because there is a thermal conductor in between, okay? And they are in thermal equilibrium. What is the meaning of that? TA is equal to TC. And here on the right side, the system B and system C are also in thermal equilibrium, okay? So here we have a conductor, okay, thermal conductor, So they are in equilibrium. It means that TB is equal to TC. Then if A and C and B and C are in thermal equilibrium, then I can write that this one, TA and TB are equal to each other. They are also in thermal equilibrium. Okay. Look at this system. Look at this one here on the right side. Here we have a thermal conductor between A and B. This is on the left side, system A with TA, and on the right side we have system B with temperature TB. And here we have system C with temperature C. Okay. So if these two systems, system A and system C, are in thermal equilibrium, and these two systems, system B and C, are in thermal equilibrium, then it means that this A and B are in thermal equilibrium. So actually, here I should talk about also the thermal conductors, thermal insulators. So thermal conductivity of each material is unique, okay? So different materials have different thermal conductivity and thermal insulating properties. If you have a perfect insulator, okay, just consider that you have a perfect thermal insulator. It means that there is no heat transfer between two systems, okay? Because here we have a thermal barrier, okay? So we will go into detail with this one. So this is the zeroth law of thermodynamics. It talks about the thermal equilibrium. Do you have any question here? Then let me continue with the temperature scales. There are three main temperature scales. One is Celsius or centigrade. The other one is Fahrenheit. The other one is Kelvin. Okay. In Turkey, Celsius or centigrade is widely used, and Kelvin is also widely used for scientific purposes. Okay. So centigrade and Kelvin are very important temperature scales. It is very easy to understand. You already know from high school years. So what is the Celsius or centigrade temperature scale? On this temperature scale, 0 degrees Celsius is the freezing point of pure water, and 100 degrees Celsius is its boiling point. Okay, but in case of Fahrenheit temperature scale, 32 degree Fahrenheit is the freezing point of pure water, and 212 degree Fahrenheit is its boiling point. So what is the difference between 0 and 100 degrees Celsius here? In case of Celsius temperature scale, delta T is 100 degrees Celsius, okay? Between the freezing and boiling point of water. But in case of Fahrenheit, the delta T between freezing and boiling point of water is 180 degree Fahrenheit. Okay, so you must be very careful, and you can convert the temperature scale from Celsius to Fahrenheit by using this formula. This is the Fahrenheit temperature. This is the Celsius temperature. You have to multiply Celsius temperature with 9 and divide by 5, and you have to add 32 degrees. Then you can find the Fahrenheit temperature. And in order to convert from Fahrenheit to Celsius, then you have to do this one. This is 5/9 times Fahrenheit temperature minus 32 degrees. Do you have any question here related to the Fahrenheit and Celsius temperature scales? Then let me continue with the Kelvin scale or absolute zero. Okay, this gives us information about Kelvin scale. Here you see a constant volume gas thermometer. Here we have a spherical shape. It has certain constant volume made from metal, okay, and it contains a gas, okay, and its volume does not change. Volume is constant. And you increase the temperature of this gas within this volume, okay? So then what will happen? The pressure measured here in the pressure gauge will increase if you increase the temperature, okay? If you increase the temperature of this gas within this constant volume, then the pressure of the gas will increase and you will see the certain pressure here. This is the pressure gauge. And on the right side, I have a graph. So what happens to the pressure? Here I have a temperature scale in centigrade or Celsius, and this is the pressure scale, okay? So here I have different types of gas. Let's say this is gas 1, and I increase the temperature from 0 degrees Celsius to the 200 degrees Celsius. What do you see? Pressure increases. Within this constant volume, the gas pressure increases. And here we have another type of gas. Here we have another type of gas, and they have also the same relation. If you increase the temperature, pressure of the gas increases. If you increase the temperature, pressure of the gas increases. But if you decrease the temperature, what will happen? Just consider that here you are using a cooling source, okay? Then you cool down the gas. Okay, so what will happen to the pressure? If you cool the gas, then pressure will decrease, and finally here at this point, gas pressure will go to zero gas pressure. And also for this gas, if you decrease the temperature, pressure decreases, and finally, when you reach to the minus 273.15 degrees Celsius, the gas pressure within this container will be zero, okay? So this temperature is called as absolute zero, okay? Because here gas pressure is zero, and in the Kelvin scale, this temperature is 0 Kelvin, okay? Here we have two scales. This is the centigrade or Celsius scale, and here we have Kelvin scale, and we have gas pressure within this container, within this constant volume as a function of temperature. And at 0 Kelvin, we have zero pressure, zero gas pressure within this constant volume, okay? And we have this relation between temperature and pressure. If you increase the temperature, you increase the pressure. If you decrease the temperature, you decrease the pressure. So this is the Kelvin scale, and you can also convert the temperature from Kelvin to Celsius, or you can convert temperature from Celsius to the Kelvin, okay? Do you have any question here? Then let me continue with the conversion. And here we have this information. Actually, we have discussed this one on the Kelvin or absolute temperature scale. 0 Kelvin is the extrapolated temperature at which a gas would exert no pressure. Here we have discussed at 0 Kelvin, the pressure of the gas is 0. So in order to convert from Celsius to Kelvin, you can use this formula. Okay, this is the temperature in Celsius scale plus 273.15. Then you can find the temperature in Kelvin scale. Here, there is important information. Let's consider that here we have ice and water in this figure. Okay, there are ice cubes, many ice cubes, and there is water. And here you see a glass thermometer and you measure the temperature of this system. Let's consider that the temperature of this system is 0 degrees Celsius, and you would like to convert this temperature to the Kelvin. What is in Kelvin? Okay, so you can use this conversion here, but you must be very careful. There is no degree symbol here. Okay, you should use just capital K. Okay, so here there's a degree symbol and this is wrong representation. Don't use degrees, okay, in Kelvin scale. In Fahrenheit scale, we have degree symbol here, you see. In Celsius scale, we have degree symbol here, but in Kelvin scale, we don't have any degree symbol. Don't use degree symbol in Kelvin scale. Okay, now let me show you relationships among Kelvin, Celsius, and Fahrenheit temperature scales. Here we have Kelvin scale on the left side. On the right, we have Fahrenheit scale. And here we have Celsius scale in between. So we know that water boils at 100 degrees Celsius. And in Kelvin scale, it is 373 Kelvin. And in Fahrenheit scale, it is 212 degree Fahrenheit. And we know that water freezes at 0 degrees Celsius, and in Kelvin scale it is 273 Kelvin. In Fahrenheit scale it is 32 degree Fahrenheit. So Fahrenheit is used in real life or not? Yes, it is used. Okay, in some countries Fahrenheit is used. In Turkey we use Celsius scale, and as I told you, Kelvin is also used in industry and science. Very important temperature scales in scientific researches. And here we have carbon dioxide. It solidifies at minus 78 degrees Celsius. Okay, and in Kelvin it is 195 Kelvin. In Fahrenheit, it has different temperature. What do you see here? Look at this temperature scales. Don't forget that Kelvin scale is never negative, okay? The lowest temperature in Kelvin scale is 0, okay? But in Celsius scale or Fahrenheit scale, we have also negative numbers below the 0, okay? Don't forget this one. And absolute 0 is this one. Absolute 0 is minus 273 degrees. What was the meaning of absolute 0? Gases have no pressure, 0 pressure at this temperature, and this is 0 Kelvin. And it is minus 460 degree Fahrenheit. So let me also show you some applications and some different materials with different boiling temperatures. Here on the left side, you see liquid helium. Actually, helium is present as a gas, okay, in air. But when you liquefy the helium, it will have this temperature, 4.2 Kelvin. It is very close to the absolute zero, okay? So you see that in Celsius, it is minus 269 degrees Celsius. It is very low temperature, okay? For this reason, liquid helium is very cold. And there is a liquid nitrogen here. It has boiling point 77 Kelvin, okay? So below this temperature, nitrogen is present in the air, okay? And this nitrogen liquefies below this temperature, 77 Kelvin, okay? It is also very cold liquid, and in Celsius, it has temperature of minus 195 degrees Celsius, very low temperature. And they are very important liquids for health applications, for industrial applications. For example, you would like to store the vaccines, you would like to store the medicines, okay? Then you would like to store some cells for scientific purposes. You can use liquid nitrogen. And liquid helium is also very important. For example, in magnetic resonance imaging in the hospitals, there are MR machines, okay, in order to take the two-dimensional pictures of the bodies. And within these systems, there are huge superconducting magnets, and these superconducting magnets are cooled by using liquid helium. So these two liquids are very important for our daily life, and they are also widely used in daily applications in industry and also science. And how to deal with this very low temperatures. I'm talking about 4.2 Kelvin. Actually, they are very dangerous liquids, okay, because they are very cold, and you must be very careful when dealing with this very cold liquids. Here, for example, on the right side, there is a diver or tank which contains liquid helium, and the temperature of this liquid helium is 4.2 Kelvin or minus 269 degrees Celsius, okay? Very low temperature. And if you are dealing with this temperatures, you must be very careful. You have to use special gloves, okay? These are made from thermally insulating materials, and you must be very careful. And in addition to that, just look at this tank. Here, within this tank on the right side, we have liquid helium, and this is the temperature. But we have overall temperature of the room is 300 Kelvin, or let's say around 27 degrees Celsius, okay? But here within this tank, temperature is 4.2 Kelvin. So in order to insulate the air and the liquid helium within this tank, you have to produce special tanks, and these tanks have also thermally insulating systems like this. Actually, within this type of dewars, there is an insulating, okay, and here outside the temperature is 300 Kelvin or 27 degrees Celsius, let's say, and here we have liquid helium and temperature is 4.2 Kelvin, okay? So this thermally insulating material can prevent very fast heating of this liquid helium. So what is used? Usually liquid nitrogen used here, or vacuum is used, okay? What is the meaning of vacuum? You have very less particles. Then you can also consider that vacuum is thermal insulator. Okay, so you can use liquid nitrogen here, or you can use vacuum. Then you insulate this liquid helium from the environmental conditions. Then you can keep this liquid helium cold for a long time. And these tanks must be very powerful against the thermal expansion. If you heat the liquid helium here, there will be gas helium. And if you further heat the liquid helium, then you will have huge gas production in a very short time. And this gas will expand and expand. Then it may explode, okay? So then you have to use very powerful materials against this huge gas increase within these helium tanks or nitrogen tanks. In addition to that, there are safety valves here, okay? And you release the increased pressure by using the safety valves. So when you are using liquid helium or liquid nitrogen, you must be very careful and you should be aware of safety issues. Do you have any question here? This is the bio application, mammalian body temperatures from the book. Most mammals maintain body temperatures in the range from 36 degrees Celsius, like humans, to 40 degrees Celsius. A high metabolic rate warms the animal from within, and insulation such as fur and body fat slows heat loss. Let's consider these animals are living in winter, and let's say outside temperature is 30 degrees Celsius, okay? And this is the body of these animals. And they have body temperature of, let's say, 38 degrees Celsius, okay? And here we have very low temperature. Here we have, let's say, relatively high temperature. How to save this temperature within this body? You need a thermal insulator. What is this thermal insulator? Fur or body fat provides this thermal insulating, okay? And look at this space application. This is the International Space Station, and there are astronauts here, and they live there. They study there. They are doing research now within this International Space Station. And what about the temperature in space? The baseline temperature of outer space is around 2.7 Kelvin. We are talking about minus 270 degrees Celsius. Okay, so how to provide living conditions within this one? Okay, you need thermal insulation. And look at the astronaut here. He or she repairing something in International Space Station, okay? And the outside temperature is around roughly 2.7 Kelvin, okay? Very low temperature, and you need thermal insulating materials. Or when space shuttles enter into the atmosphere of the world, their temperature rises up to very high temperatures, okay? And you have to use very good thermally insulating materials, okay? And also in industrial applications, these things are very important. Do you have any question? Okay, let me continue with thermal expansion. What is thermal expansion? If you increase the temperature of material, then its volume expands. Its volume increases, okay? And if you decrease the temperature, then its volume shrinks. Thermal expansion, thermal shrinking. They are very important in industry, in engineering. And here on the right side, I have already mentioned, you see a gas thermometer. There is a container and it contains a gas. If you heat this gas, if you increase the temperature of this gas, then the gas within this material expands, okay, and then pressure increases, okay. And here we have bimetallic strip. We have two metals, and if you heat these metals, then they will expand, okay. So this is the thermal expansion, and we have also many examples in our real life. For example, if you have a completely filled and tightly capped bottle of water, let's consider this part is tightly capped, and then you have water within this bottle, and if you heat this water, then the material will expand, and finally you can crack this bottle. Or, as I told you, in case of helium or nitrogen dewars, okay, there are release valves, so you can decrease the pressure within the dewar. But if you don't have any valve here, and if they are closed, and helium vaporizes, and the pressure increases, and this tank can explode like a bomb, okay? So the pressure can crack this dewar. And you can use this thermal expansion property to loosen a metal jar lid by running hot water over it. So let's consider that this white lid is very tight and you cannot open it. And if you drop hot water, okay, on this metals, then they will expand and you can easily open them. So there are many applications, but you must be very careful with thermal expansion in our real life in industry. For example, you are designing or producing an engine in industry, okay? And the temperature in the engine changes by time. So let's consider engine in ships, engine in submarines, engine in planes, okay? Or engine in missiles, or engine in motors, in cars. So you use metals, and thermal expansion of these metals are very important because temperature of the engine changes a lot, okay? At the beginning, it is, let's say, cold at room temperature, and then it reaches up to very high temperatures, and thermal expansion becomes very important for engineering applications. And let me continue with the linear thermal expansion. So if you increase the temperature of a rod, then its length will increase. It will be expanded, okay? So how to define this change in length? It is given with this equation here. This is delta L, the change in the length of the rod, and this is the alpha, coefficient of linear expansion, and it is specific for each material, okay? Each material has certain coefficient of linear expansion. Here we have L0, this is the original length, and this is the delta T, change in the temperature. So you change the temperature of the rod, then you change its length. Here we have example. There is a rod here, and the length of this rod at the beginning is L0. This is the initial length, and temperature is T0. Okay, let's consider 300 Kelvin, room temperature. Okay, and you heat this rod and you increase the temperature. Now the temperature is higher than the room temperature, and we have here delta L. there is an expansion, and this delta L is given with this one. So if you increase the temperature, then the length will increase. It's vice versa. If you decrease the temperature, then the length will decrease. So if you increase the temperature with 2 delta T, then the length will increase with 2 delta L, because this delta L on the left side of the equation is directly proportional to the delta T. Okay? And what about the initial length here? Here you see initial length, L0, this one. Okay? So we have here a rod. It has certain L0 initial length, and temperature is T0, and I increase the temperature. Then it is expanded. This is the new length of the rod. And here we have rod from the same material, but now length is 2 times bigger than the initial one, and temperature is again the same, and I increase the temperature with the same amount here, which I have increased. What do you see here? The increase in the length is given with 2 delta L compared to this one, because delta L is given with alpha L0 delta T. It is directly proportional to the initial length. If you have 2 L0 here, then here you will have 2 delta L. This is the linear thermal expansion. So due to the temperature increase, material expands. If you decrease the temperature of the material, then temperature can shrink. And what about the molecular basis of thermal expansion? Here you can consider that there is a crystal, and these are the atoms on the corners. Okay. And let's consider that these atoms are connected by springs. Okay, actually this is not the case, but this is just representation. And this is the average distance between the atoms, this one. Okay, when the temperature increases, the average distance between atoms also increases. Okay, and with this one, atoms get farther apart and every dimension changes. Just look at this one. Here, just consider we have a material with this shape. And within this material, we have millions of atoms, and between atoms, we have this certain distance. Okay, if you increase the temperature, okay, then this average distance between atoms increases, and then material expands. Now this is the new dimension of the material after heating, okay, because temperature changed. Okay, this is the explanation in molecular basis. So what happens to the average distance between atoms? This is the potential energy of the 2-atom system, let's say, and this is the distance between the atoms. And during the last lecture, we have seen that the potential energy between 2 atoms is given with this relation. And here we have an average distance, equilibrium distance, okay? So here, at this condition, we have minimum energy, okay, minimum energy, and atoms are happy to stay at this condition with some certain average distance between them. So if you increase the temperature, you increase the energy of the system, okay, then we have Neave energy, then this is the average distance between the atoms here. In equilibrium, we have this average distance. X is this one, X equilibrium, let's say X1. And if you increase the energy of the system, if you increase the temperature of the system, then average distance will be like this. And if you further increase the temperature of the system, average distance will be like this. If you further increase the temperature of the system, if you further increase the energy, then this is the average distance between the atoms. So what will happen? This average distance will increase, okay? Then in total, material will expand. This is the explanation of thermal expansion in molecular basis. And what about the expansion of holes and volume expansion? It is very important. Here we have a cold material, or let's say the temperature is around room temperature, 300 Kelvin, or let's say 27 degrees Celsius, and you heat this material, and now it is hot, okay? So the new temperature, let's say 400 Kelvin, okay? Or you can also convert into the degrees Celsius, and now we have bigger volume, okay? Material is expanded, right? But what happens if we have a hole within this material? The hole within this material will also expand, okay? Don't forget this one. This is very important. Sometimes students think that this hole will be smaller after thermal expansion, but this is not correct. The hole will also expand, okay? Now we will have bigger hole within the material after thermal expansion, because just consider that here we have atoms, okay? And after heating, the average distance between atoms increases, okay? So this is the new situation after thermal expansion. And here we have atoms. They have certain average distance in equilibrium condition, and after thermal expansion, the average distance between the atoms is increased, okay? You can consider like this. And what about the volume expansion? This is the equation for the linear expansion, and delta L changes by temperature, okay? This is the linear thermal expansion. And what about the volume thermal expansion? It is given with delta V change in volume. It is equal to beta, coefficient of volume expansion. This is V0, original volume, initial volume, and this is the delta T, change in the temperature or temperature change. This is the volume expansion. And here we have coefficient of linear expansion. It is very important table for technological industrial applications and also for daily life. So each material has certain unique alpha, okay? So you change the temperature of the aluminum, for example. Let's say you change its temperature 100 Kelvin or 100 degrees Celsius, then its length will increase, but with the same change in the temperature of the glass. Let's say again delta T is 100 Kelvin. So you have same delta T, you have same L0, but you will have different delta L. You will have different linear expansion because glass has much lower linear expansion coefficient compared to the aluminum or brass, okay? So you provide same delta T, you increase the temperature in same amount, but the expansion is different because linear expansion coefficient is different. And here we have quartz, fused quartz, so it has very low thermal expansion. And for technological applications, look at this one. For military applications, for technological applications, this information is very important, okay? So very low thermal expansion coefficient is required for some applications. So here there is another special material. The name is INVAR. It comes from the invariable değişmez. Okay, this is the special nickel iron alloy, and it has very low linear expansion coefficient compared to the aluminum, compared to the copper, compared to the pure nickel, compared to the pure iron. It has different thermal expansion coefficient and very useful material for industrial applications. Okay, so for industrial applications, you need very low thermal expansion coefficient material. Otherwise, when the temperature of the material changes, then its shape will change, and it is very bad for some applications. Just consider satellites, okay? Just consider that this is the Earth, and here there is a satellite. These are the panels, solar cell panels, let's say, okay? And within the satellite, just consider you have a camera. Just consider you have sensors, okay? And other electronics. What is the temperature in space? Baseline temperature is around 2.7 Kelvin, let's say, okay? And there is also sun, and the radiation comes from the sun can increase the temperature of this satellite up to, let's say, 400 Kelvin, okay? Then what do you see here? Every part within this satellite in space, the parts in the camera, the parts in the sensors, and also electronics part will have this temperature change many times per day, okay? So they are cooled and they are heated. They are cooled, they are heated. So with this temperature change, the camera shouldn't be affected. Sensors shouldn't be affected. Electronics shouldn't be affected, okay? So it is very important to use low linear expansion coefficient material in this type of applications, okay? I will not go into detail, but for real life, this information is very important. And here we have, again, coefficients of volume expansion. Again, here you see beta value of, this was volume expansion, beta initial volume, and change in the temperature, okay? So if you have low beta, then you will have low thermal expansion in the volume. So we have brass, we have copper, these are the metals. They have more or less same volume expansion coefficient. Here we have glass, relatively low. Here we have INVAR, again, iron nickel alloy, which I have discussed here. Very important technological material. Here we have a quartz, even lower, okay? And here we have steel, it is also metal, okay? So you see different coefficients of volume expansion. And let's discuss some examples of thermal expansion. This is the railroad track, and this is the metal, okay? If you use high thermal expansion material here, then the road will be destroyed. during hot days, and during cold days, the volume shrinking will occur, okay? So then you can destroy the railroad. This is very important, and you have to use special materials, special steels, special alloys for these applications if there is huge thermal changes in the system. So what do you see here? There is a gap, okay? And this gap is used against thermal expansion. So on hot days, the segments expand and fill in the gap. If there were no gaps, the track could buckle under very hot conditions. And look at the bridges. Maybe you always see these gaps in the bridges. There is a huge gap, and during the hot days, this gap will decrease, and cold days, this gap will increase. Okay, if you don't put these gaps on bridges, then they can collapse. So look at this part of joints in buildings. Okay, there is a gap here between two parts of the building in hospitals, in university buildings, in shopping centers. I mean, in big buildings, you always see these joints, and these parts against thermal expansion. Okay, if you don't use these joints, then the building can collapse. So this is the example of thermal expansion, and let's discuss the thermal expansion of water. So what we have discussed up to now, that if you heat a material, if you increase the temperature of the material, then material will expand. If you cool down the material, then material will shrink. But water is exception. What happens in water between 0 degrees Celsius and 4 degrees Celsius? Water decreases in volume with increasing temperature. So here on the top picture, you see water volume versus temperature. This is the 0 degrees Celsius, this is 100 degrees Celsius. And what do you see here? That the water volume increases with temperature. Water expands as temperature increases. But at this low temperatures here in this region, water has different behavior. This is the volume, this is the temperature, and between 0 degrees Celsius and 4 degrees Celsius, what happens? You increase the temperature, okay, delta T is increased, it is positive, but volume decreases. What do you see here? Delta V, beta, V0, delta T. You increase the delta T, then you should increase the delta V, but between 0 and 4 degrees, it works vice versa, okay, in water. Because water is an exceptional case for this thermal expansion, okay? And this property of the water is very important for the life in lakes, okay? With this property, because of this anomalous behavior, lakes freeze from the top down instead of from the bottom up. So this is the exceptional case in thermal expansion. And let me continue with the thermal stress. What is thermal stress? Here you see again a bridge. This is one part of the bridge road. This is another part of the bridge road. And here we have a gap. Okay. And during the hot days, this gap will decrease. During the cold days, this gap will decrease. Okay. And if you don't use this gap, just consider that you are building road like this. and there is no gap here due to the thermal expansion. Due to the thermal expansion during the hot days, they will apply force each other, and then this bridge can be broken, can collapse. Okay? For this reason, we use expansion joints in civil engineering. Expansion joints on bridges are needed to accommodate changes in length that result from thermal expansion. And what about this thermal stress applied on the neighboring part of the road due to the temperature change, which is given with this one? This is the thermal stress force needed to keep length of road constant, and this is the cross-sectional area of road. This is the Young's modulus, which we have discussed in previous lectures. This is the coefficient of linear expansion, and this is the temperature change. So if you increase the temperature, then we have a thermal stress. Okay, we have a thermal stress, and you have to use expansion joints on bridges, on buildings against this thermal stress. So let me discuss an example here. An aluminum cylinder, 10 centimeter long, with a cross-sectional area of 20 square centimeter. Here we have an aluminum rod. Okay, initial length is 10 centimeter, and the cross-sectional area is given 20 square centimeter. It is used as a spacer between two steel walls. And here we have a steel wall, okay, and here we have another steel wall. At 17.2 degrees Celsius, it just slips between the walls. So this aluminum can move easily, okay, at 17.2 degrees Celsius. But what happens if you increase the temperature up to 22.3 degrees Celsius? Calculate the stress in the cylinder and the total force it exerts on each wall when it warms to 22.3 degrees, assuming that the walls are perfectly rigid and a constant distance apart. So at this temperature, 17.2 degrees Celsius, this aluminum rod can move up and down easily, and you increase the temperature to this value, then what you expect, this rod will expand. So new length will be bigger than this previous length, okay? Then you cannot move this aluminum rod anymore. So what about the calculations? If you know the thermal stress formula, which we have seen in the previous transparency, it is easy to calculate it. This is the thermal stress, force per area, Young modulus of aluminum, linear thermal expansion coefficient of aluminum, and the change in the temperature. So this is the final temperature. This is the initial temperature, 22.3 degrees Celsius minus 17.2 degrees Celsius, and the change in the temperature delta T is 5.1 degrees Celsius or 5.1 Kelvin. Okay, then just put the Young modulus of aluminum here, 7 times 10 to 10 Pascal, and just put the linear expansion coefficient of aluminum here, 2.4 times 10 to minus 5, 1 over Kelvin, and just put here the delta T, change in the temperature. Then the stress can be calculated as minus 8.6 times 10 to 6 Pascal. Okay, so What about the force? The total force is the cross-sectional area times the stress. So we have found the stress here. Okay, we have calculated the stress, and then it is given with force per area, and I have calculated stress, and I know the cross-sectional area, then I can calculate the force. And force is this one, minus 1.7 times 10 to 4 Newton, or minus 1.9 tons. It is huge. This small cylinder applies huge force, okay, if you change the temperature. So when you are designing an equipment or an engine in industry, in engineering, okay, you must be very careful. So just consider aluminum engines used in cars, okay? So even very small change in temperature, so 5 degrees Celsius change in the temperature can produce huge thermal stress. You must be very careful. Okay, let me continue with the heat. Do you have any question until this part? So let's discuss the quantity of heat. Sir James Joule in 19th century, end of 19th century, studied how water can be warmed by vigorous stirring with a paddle wheel. Here we have a water within a bottle, okay, and here we have a paddle wheel. You see, there is a paddle wheel, and this is connected to this one with a rope, and rope is attached to this mass here, and this mass goes down and it is rotated. Then paddle wheel within the water is also rotated very fast, okay? So the water warms as the paddle does work on it. So what do you see here? We have a weight which is given with mg, right? And let's say this is y is equal to 0 ground, and this is the y is equal to y1, okay? And what about the work? Work is given with force times displacement, okay? Then force is given with this one, displacement is this one, and then we have a work, okay? So the water warms as the paddle does work on it. The temperature rise is proportional to the amount of work done. If you put here a temperature source, okay, then you can also produce the change in the temperature. So here we have a definition. The calorie, abbreviated cal, is the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to the 15.5 degrees Celsius. So what about the change in the water temperature? 1 degree Celsius. You have 1 gram water and you would like to change its temperature 1 degree Celsius, and it is called as 1 calorie. Okay, this is the amount of heat required to raise the temperature of 1 gram water from 14.5 degrees Celsius to 15.5 degrees Celsius. So now let me continue with the quantity of heat Q. So here we have heat required to change the temperature of a certain mass. Here we have water, it has certain mass, and I would like to change its temperature, okay? Then I need heat, okay? So the quantity of heat Q required to increase the temperature of a mass M of a certain material by delta T. Here I have a bottle of water and its mass is m, and I would like to increase its temperature with delta T, then I need heat to increase this temperature, and this heat required to change the temperature is given with this equation. You already know from high school years, m times c times delta T. This is the change in the temperature. This C is specific heat of material, and it is also unique for each material, and this is mass of the material. So for water, for example, the specific heat of water is approximately 4,190 joule per kilogram per Kelvin. Let me continue with this example 17.6 from the book Overheating Electronics. This is very important for daily life. You are designing an electronic circuit element made of 23 milligram of silicon. Mass is here, silicon material, which is mostly used in electronic circuits. The electric current through it adds energy at the rate of 7.4 milliwatt or 7.4 times 10 to minus 3 joule per second if your design doesn't allow any heat transfer out of the element. At what rate does its temperature increase? The specific heat of silicon is given. So just consider that here you have a silicon board, and here you have conducting lines. Okay, so you apply voltage between these two ends of the wire, and then there is a certain current. Okay, so due to this current, this material will be hot. Okay, and then if you don't use any cooling sources, then this will damage your electronics. For this reason, electronics parts usually cooled by using fans or by using other metal coolers, okay, with specific design. So let me solve the question and then talk about its importance in electronics. So what about the formula? Remember the formula. Q is given with mc delta T. Okay, what is given here? We add the energy at the rate of 7.4 milliwatt or 7.4 times 10 to minus 3 joule per second. So we have this one. You give the energy into the system. It is given. Okay, and this one is asked. What is the change in the temperature by time? So if you divide this one with dt, if you divide this one dt, then you can write this expression. So this is asked, this is given in the question, 7.4 times 10 to minus 3 joule per second. Mass is given 23 gram. You have to convert this one into the kilogram. Then here we have specific heat of silicon, C, which is given in the question. Then this is the rate of change of temperature. What do you see here? The temperature changes by time with this relation, 4.46 Kelvin per second. It means that 27 Kelvin per minute or 27 degrees Celsius per minute. Let's consider you have electronics, okay? And the temperature is 27 degrees Celsius at the beginning, and you drive current, then So each 1 minute, you increase temperature 27 degrees Celsius. So after 1 minute, the temperature is 54 degrees Celsius. And after 2 minutes, what is the temperature? The new temperature of the system is 81 degrees Celsius. So you can destroy the electronics, okay? This is huge temperature. Within 2 minutes, the temperature increases up to 80 degrees Celsius and very dangerous for the electronics. And usually in electronics, coolers are used, okay? If you open your computers, you will see this type of coolers on the motherboard or in other electronics, and usually special design used in electronics. For example, what you see here, we have many circuit elements, capacitors, resistors, and what else? Inductors. So we have many circuit elements here. And in addition to that, here we have an aluminum block. What is the duty of this one? This is the cooler, okay? This is a metal cooler, so it has many surfaces. So via these surfaces, it interacts with the air and then cools down the temperature of the circuit board. And this type of coolers you can see more or less in every circuit element. Let's talk about the molar heat capacity. The quantity of heat required to increase the temperature of n moles of a certain material by delta T. So I have a material and it has molar heat capacity C, and I would like to increase its temperature, okay? And this is the number of moles of material, this N here. So the quantity of heat required to change the temperature of a certain number of moles is given with this expression. For example, here we have molar heat capacity of water. It is approximately equal to 75.4 joule per mole per Kelvin. So what do you see here? We have a table for specific heats and molar heat capacities. On the left column here, we have specific heat C. And here on the right column, we have molar heat capacity, capital C. Okay, so again, you see that each material has different specific heats and specific molar heat capacities. Here we have aluminum, beryllium, copper, and what do you see here? This ethanol and ethylene glycol have very huge specific heats and also very huge molar heat capacities compared to the other materials. And here we have water, for example, liquid. It is around 75. Look at the aluminum. Compare the aluminum and water. Water has 3 times bigger, more or less, molar heat capacity compared to the aluminum. Okay, look at the iron. So it is also around 26. And what else? Here we have lead, and here we have copper. Metals usually have more or less the same magnitude of molar heat capacity, let's say. And here we have water, which is quite different. We have marble here, quite different. And here we have ethanol, which has quite different molar heat capacity. And in applications, these properties are very important in industrial applications. And here I have last transparency. Here we have a glass and we have water within the glass, and you would like to change temperature of this water within this glass. So then we have this relation. I would like to increase the temperature of the water, and how much heat is required to produce this change in the temperature of water? Water has a much higher specific heat than the glass or metals I have discussed here. This is the water, and these are the metals. And water has more or less 3 times bigger molar heat capacity compared to the metals, and used to make cookware. For example, in kitchen, usually we use glass materials or metal materials to make cookware, right? So, and then this helps explain why it takes several minutes to boil water on a stove, even though the pot or kettle reaches a high temperature very quickly. So you can change the temperature of metal objects quickly. Why? Look at the formula. Let's consider you would like to produce temperature change 100 degrees Celsius of aluminum pot, let's say. This is aluminum pot, and you would like to increase its temperature with 100 degrees Celsius. And what about the molar heat capacity of aluminum? It is around 25, let's say. Okay, here, where is it? Aluminum, 24.6 molar heat capacity. And this is the heat required to produce this change. So this aluminum has 25. Just consider water, and here within the aluminum pot, you have water, and water has around 75 molar heat capacity, and you would like to produce same temperature change, 100 degrees Celsius, this is delta T, this is C of water, and let's say same N number. And what about the Q? For the water, you need much higher Q compared to the aluminum, okay? So you need more heat. For this reason, it takes several minutes to boil water on a stove, even though the pot or kettle reaches a high temperature very quickly. So you can produce this huge temperature change in aluminum or glass, okay? But in water, it requires more heat. So with this one, I finished my lecture. Take care of yourself. Bye-bye.